So EDM lecture number 16, batteries, capacitors, and this is an abbreviation for the cool kids, CAP networks, capacitor networks. Okay, so I started by saying that there was some basic background ideas, so let me just repeat them. So big background ideas. If I have two conductors, right, so here's a conductor and here's another conductor. They don't have a special shape, they're just sort of like two lumps of metal, but they are insulated from each other. So let me put insulated from each other. This actually is a capacitor. And I said that wires are just long pieces of wire, long pieces of conductor. So let me smooth out from this conductor a wire, right? So, you know, metal's a malleable, so you could like pinch and pull, like taffy, sort of. And let me pinch and pull a wire from this conductor. So since this conductor is touching this other conductor, all of this object is all at the same potential. So if I call this conductor A, this thing might have potential V sub A. And if I call this object, including the wire, because the wire is touching, which is a conducting contact between this piece of metal and that piece of metal. So really this is one conductor, one piece of metal, and it's in general got a different potential. So this is VA and VB. And there is a potential difference. So I could say that the potential difference from B to A is the potential at B minus the potential at A. And let's just say that the way that this world works out, the way the charges are distributed, let's on this capacitor, which has a net charge equal to 0, there is a charge Q sub B over here and a charge Q sub A over here. So the net charge equaling 0 is the situation where QA equals the opposite of QB. For example, let's say that QB is the positive charge. Then that means, right, that implies, so if QB is the positive charge, then negative, the positive charge is negative charge. So QA will be less than 0. And remember that E field points from plus to minus, and also E field points from high potential to low potential. So I might say higher and lower because they're just relative terms. It's not the highest potential to the lowest, it's just a higher potential to a lower potential. So there's a lot of sort of like little background ideas going on in here. Some assumptions like the net charge is 0. Yeah, this is going to help you think about capacitance and especially capacitor networks. Okay, so the electric field points from high potential to low potential. It also points from positive charge to negative charge, or more positive charge to more negative charge, or higher charge to lower charge. So here is a rough sort of picture of the electric field in between the capacitor. And the field lines could be other field lines like this. And since the net charge of this capacitor object, right, which is the two conductors together, since the net charge is 0, these field lines, if a field line leaves the B conductor, because the net charge is 0, it's always got a negative charge to fall into. So none of these field lines actually make it all the way to infinity without coming back. That's a kind of a weird thing to say, but the field lines are going to emerge or source out of the positive charge, and all of them are going to sink into this negative charge. Okay, all right, so this is some background idea. So the next background idea is to add in what's known as a battery. And so you might wonder, okay, so how did I get this charge separation, right, where the net charge is still 0? I got some sort of charge separation. And one of the ways that I can cause that to happen is by using a battery. Batteries can cause the charge separation on capacitors. So they can cause it and maintain tirelessly the charge separation on capacitors. So, yeah, what they do is they provide what's sort of quickly described as voltage, but there's some problems with this. I think, but I'm going to use it anyways because everybody does. So what they do is they provide voltage. They enforce, and they could possibly actually use force. They use energy and force, right? Force to do work. They enforce a potential difference. And so let's pretend. So this is my cartoon drawing of a battery. Batteries have positive terminals and they have negative terminals. And another thing that they do is they provide the voltage, and often this little cartoon label is labeled by the voltage or the potential difference that it enforces. And so this little thing right here actually is a small conductor. This is a different small conductor, and they are separated by some sort of electrical machine in a real sense. It's like a little thing that pushes electrons from the positive terminal internally to the negative terminal and maintains this terminal as negatively charged and this terminal as the equivalent opposite. So this is a little 5 minus sign, so let me put 5 plus signs over here so that the battery overall has net charge equal to 0. So this is an idealized assumption that makes everything conceptually easier, but you don't actually have to have batteries have net charge equal to 0. They can have a net charge, and nonetheless, this battery will do the job of maintaining the proper potential difference between the high conductor and the low conductor. And so what you can do is you can actually take this battery and use it to have caused this potential difference. If you remember though, QB was the positive charge, QA was the negative charge, so I'm going to have to take this battery and turn it around in order to cause this charge separation. So let me use the ductility of these metal wires, these conductors, and move them, right, bend them so that they go to the terminals of my cartoon battery. So remember, this has to be the positive terminal, and this is the negative terminal. And I make the conductors touch. And so right now, if this is a 5-volt battery, then depending on the capacitance of this capacitor arrangement, there's going to be a certain charge that shows up separated on my two conductors. And this 5 volts is the potential difference between the two conductors VB and VA, right? So, and this is a plus sign when you take the high value of potential and subtract off the low value of the potential. So this 5 volts. Okay. Yeah, so in a sense, this thing right here is all, let me kind of like shade it in. All of this is all one conductor, and all of this is a separate conductor. And I hope you can see that with this red line, I have two separate conductors being maintained at a potential difference. There is a diagram that we can use that's much simpler to draw than this cartoon, although the cartoon actually more resembles a physical situation. The diagram looks instead like this. Here's the capacitor. A capacitor is got a diagrammatic symbol that's supposed to remind you of two parallel plates. Looks like the parallel plate capacitor, and I'm going to label it with its capacitance C. And then with wires, I'm going to go, right, these are thin lines. They go from one side of the capacitor to the negative terminal of a battery, which is drawn as a short line. The long line is the positive terminal of the battery. So these are the plus and the minus sides of the battery, this thing here. And you just complete our circuit to the other side of the capacitor with a different wire. So I've got, quite literally, I've got two conductors. I've got a conductor on the right-hand side, and I've got a conductor on the left-hand side. This is what these red circles are indicating. Down here, diagrammatically, I could say that this thing's got a potential difference called capital V, which I labeled over here, or gave a value to 5 volts. Up here on this capacitor, there is a charge Q that's the positive version of the charge, and a charge negative Q on the other plate, so that the net charge of the capacitor is 0, right? And this capacitor, remember, capacitance is the charge that you can separate, which is Q. It's not 2Q. It sort of looks like the difference in charge is 2Q. You might wonder if that's the charge separation. That's not the charge separation. The charge separation is just the charge of, it's taken as the charge of the positive plate in the case where we're talking about capacitors with no net charge, but it's Q over V. So this is our diagram, and you can see that this is actually quite simple looking, but I hope that the past, I don't know how long I've been talking, but 15 minutes of talking, there's a crap ton of physics in all of this 15 minutes. This diagram is full of physics. It's full of assumptions and idealizations, but this is the level at which we're going to work conceptually now, but underpinning all of that really is quite a lot of detail. Okay, so let's start with an example, super simple example. Here is a capacitor, so I'm gonna take this diagram and I'm gonna turn it a little bit like this and kind of manipulate it a little bit. I'm gonna point the battery the different direction and mess around. So let's point the battery this way. So here's the battery with some wires. Here is, I'm going to put actually the capacitor here. So here is the capacitor, and since it's simple, let's just have a battery and a capacitor. So I've got the capacitor and the battery, and the rest of the drawing is just a wire to finish it out. So let's say that this battery is described by V here, and this capacitor is described by C, and we'll say that the battery is maintaining, say, easy number, 10 volts, right, 10 joules per coulomb, and this capacitance, so realistic capacitors in actual laboratory settings, you can have quite large capacitances, but a large capacitance, honestly, is somewhere like in the microfarads or something like that, a large conventional capacitor. So let's say it's a 2 microfarad capacitor, and the question is, what is the charge on the lower capacitor plate? Right, so the question is what is the charge on the lower capacitor plate there? So really quickly, so a quick thought is, I wonder what the sign of the charge is. So let me look up here in my drawing. Here's the battery. It's got a positive side. The long plate is the positive side. And the short little plate is the negative side. So up here, if you remind yourself of how things would work out, right? This battery maintains a particular, or it maintains a potential difference by causing the negative terminal to have the appropriate negative charge and the positive terminal to have the appropriate positive charge, such that the net charge is 0. So that means whatever is connected to the negative terminal is the negative side. So can you see that by a wire, the negative terminal is connected to this lower plate. So this Q, one of the things I can say immediately is Q is less than 0. That's the negative side. But I wonder, so now let's figure out the actual charge, right? So we know the sign, we expect it to be negative. So remember that C is Q per V. So the amount of charge, we'll have to be careful because I labeled this as Q when in the drawing over here it's really the negative Q. But I'm going to be a physicist and just keep that as a thing that I know I need to worry about. So over here you can solve for Q really quickly. It's equal to C times V, and C is 2 microfarads, and V is 10 volts, and you get 20 microfarads volts. So what's a microfarad volt? The SI unit of the farad, right? So the farad is the SI unit of capacitance, which means that the farad, so 1 farad equals 1 coulomb over 1 volt, like this. So simply, microfarads times volts is microcoulombs, right? So that's the answer to the charge separation. This is the charge separation. And what this leads me to say is that the lower plate has charge negative 20 microcoulombs, and this is the answer to this question here, this simple example question. Let me point out something that some students, I certainly find it super useful to do this. Some people never find it useful, but maybe you will. I think it's really cool to do the following thing. Let me actually redraw this picture. So this picture has a battery, like this, a capacitor like this. And so here's the battery, here's the capacitor. I'd like you to notice that there are two, and there are only two conductors. The two conductors could be labeled A and B. And in a funny way, check this out. Like, I'm gonna, yeah, let me do it just because it's funny to do. So this battery right here, let me draw it. Here's the battery. And the other thing that is interesting in this problem is this capacitor. So the conductor I marked A is actually a piece of metal that goes from the positive terminal of the battery, right, via this wire to this upper plate of the capacitor. This is all just some lump of metal called A. And there's another lump of metal, which is from the negative terminal of the battery all the way around to the other plate of the capacitor, which is insulated or separated from the upper plate of the capacitor. So let me draw that lump of metal. Here. It's not a very clean looking diagram, but this is all the conductor B. And because of the orientation of the battery, that the lower plate is positive, of the battery here, that means that all of this conductor, this is the higher potential conductor because the battery's positive plate is touching it. So this is the higher potential conductor, and the conductor B is the lower potential conductor, right? And VA minus VB is a positive number because A is higher and B is lower, and VA minus VB is equal to the voltage of the battery. So if this battery has voltage V, this is the capacitor with capacitance C. This might be useful, and I'm probably going to use this kind of a language when I talk about capacitor networks, which is the next topic. Okay, so capacitor networks. Two basic, and I'm going to use a word that's actually very mathematical. It's got a pretty tidy mathematical definition, and if you want to go look up the math definition of it, you can, but I'm going to use it here. There's two basic topologies for capacitor networks. And the topologies, another way to say that is connections, connection shapes, or something like that. But anyways, two basic different topologies or connections for cap networks. They are called series and parallel. The series shape takes two, in general, different capacitors. Here's a capacitor. Let's call it C1. And here's another capacitor, C2. And if I want to connect these in series, what I do is this. where I'm going to take these two capacitors connected this way and put them over some maintainer of potential difference. So I put these in series. The idea is I only have sort of one path from the battery through both capacitors back to the battery. There's only one way to do that. That's series. That's the topology of the series. There's only one way to do it, one connection path through both capacitors and the battery. In parallel, though, this one will get a little bit complicated looking. Yeah, I'll just draw this capacitor here, and I'll kind of do the same thing. So this capacitor over here. What I need to do is I need to make sure that there are two ways to get from the battery through both capacitors. I want two different ways. So what I'm going to do is this, and this looks weird. First, I'm going to parallelize the two capacitors. That means that the two capacitors are actually their own little loop already. And I'm going to take one of the connections between the capacitors and connect it to one side of the battery. And I'm going to take the other connection between the capacitors, right? This is a different conductor. This is a different conductor than this conductor, and connect it to the other side of the battery. And the sense in which I have two different parallel paths from the battery through, so the idea here, actually, it turns out, I was probably misspeaking before, but if I go from the battery, I can either go through the lower capacitor and back, or through the upper capacitor and back. That is, I can choose a path that skips one capacitor but can't skip the other. Okay, so this will be C1 and C2. So same capacitors, 1 and 2, but connected in completely different ways. So it turns out, for the series case, let me give you the answer. In this series case, I'm going to replace the two separate capacitors as one effective capacitance called C effective. So in a sense, what I'm doing is I am trying to forget the fact that I have two separate capacitors connected in series, and instead I'm going to understand the two separate capacitors as a single effective capacitance. So from here to here is here, and I'll say this is A and B, A and B. And inside of this red vague circle is actually these two capacitances. It turns out that the relationship between C effective and the values of C1 and C2 that relationship is actually independent of whatever is happening on the outside of the series. And it's a strange relationship. So 1 over C effective is 1 over C1 plus 1 over C2. This is the answer. In this case right here, instead, so let me draw a divider. So we're talking about series here and parallel here. I can talk about a place B and a place A. So this is all, if you look at it, I think this, well, actually, yeah, I'm not going to bring that up yet. So I would like to understand in between A and B, I want to understand these two capacitors connected in parallel as an effective capacitance. But because I have a different topology, even if I have the same capacitors, I have them hooked up differently so that the way the charge is going to separate is going to be different in this case versus that case because of the difference in connections, difference in the topologies. So this C effective is going to be a little bit different looking. So same battery, same idea. So I've got B and A. So inside of this circle is a capacitor, or an effective capacitance. That is the effective capacitance of the capacitors hooked up like this, right, in parallel. And it turns out that this is a very different looking answer. And you have to be super careful. This is different. So let's run through the derivations of the series and parallel rules. The parallel rule is the simpler one. You get this effective capacitance, which is simply just you add the two capacitances together. So here is, I wanted to put the labels out to the side because I'd like to fill in this drawing with other details like charge and voltage, or potential differences. So yeah, so C1, this is the upper capacitor, C1, and the lower capacitor, C2, in parallel. The series relationship for the effective capacitance was really different looking. It amounts to, I'm doing one step of algebra from the previous page. What you do is 1 over C1 plus 1 over C2. And as written, this is actually incorrect, because I'm saying that farads is the same as 1 over farads, but it's not. It's a common mistake for students when they're calculating to forget that -1. You will always know that you forgot it if you include units when you are filling in for your calculations. But if you don't work with units, which many students don't, they put in units later, you'll miss the fact that you forgot to invert this square bracket. Okay, so that this -1 is tends to be forgotten by a lot of people. Okay, so I'd like you to notice that I am starting with no battery. You see this, there's no battery in either of these situations. And the reason I want to start there is because I want to know what is the charge and also what is the potential difference between everything. In this picture right here, I'm going to start with no net charge on capacitor 1 and no net charge on capacitor 2. So the charge of everything is just simply 0. There is no potential difference amongst any of the conductors, even though I have 1, 2, 3 separate conductors. So maybe I'll go A, B, and C. So there is no potential difference anywhere. Okay, so it's funny I'm going to use this, but in parallel, let me go over here. I've got a really different looking problem. No battery, 2 capacitors, but the hookup is really different. I've actually only got 2 conductors in this case. In the series position, or the series shape, I actually have 3 separate conductors. I've got this piece of metal, I've got the middle piece of metal, and I've got the right side piece of metal. But over here, if you look, I can draw a clean line down through the middle of the capacitor gaps and the place where I'm going to insert a battery later. And this is just 2 pieces of metal, purely. So I've only got 2 conductors. In this arrangement here, when I add the battery, so let me put in the battery. So I'm going to put the positive plate on the left side in this case. So there's the negative plate. Now I'm going to enforce a potential difference. And if the battery has voltage V, then the potential difference is such that VA and VB are different by V. So V equals VA minus VB. So this position A here is marking the conductor A. So I can actually imagine this dot being anywhere. So let me put it here. So this right here must be the potential of the left-hand side of capacitor number 2. And this little dot here is a dot B, which is different, right? It's a different potential value than A. So the right-hand side plate of this capacitor C2 is VB. That is, the potential difference across C2 is also equal to VA minus VB. It's just the battery voltage. That is, the capacitor C2 sees all of the voltage of the battery. You can check C1 as well. The potential difference across C1, well, this is all the same conductor. So this is also conductor A, and this is conductor B. So it's the same story that plays out. The potential across C1, or the potential difference across C1, is again VA minus VB, is all of the battery voltage. So even though this capacitor is far away from this battery, this capacitor sees the same potential difference as this capacitor. It's very different in this case. In this case, when I add the battery, so let me put the battery in. In this case, this is very different. Check this out. So this potential is actually equal to the battery voltage. So notice I put the high side on the left again. The positive long plate of the battery is on the left side. So this left capacitor plate is going to be the positively charged plate. It's the higher potential plate. So V actually is VA minus VC. Not B, but C, because the battery is connected to the conductor A and the conductor C, but the battery is not connected to the conductor B at all. So B is floating in the middle. It's actually got a middle value of potential. So this is VA minus VC. So this is some trickery, but watch this. If I look at VA minus VB plus VB minus VC, can you see that this is actually equal? This is a little bit of a trick. But VA minus VB is the potential difference. Here's A and here's B. It's the potential difference across C1. VB minus VC, VB minus VC is the potential difference across C2. If you group them together. So the battery voltage is shared in series. The battery voltage in parallel is not shared in parallel. So the sense in which it's shared is the battery voltage is the sum of the voltages across C1 and C2. The language goes, the battery provides a rise in potential as you go from negative to positive, and then you drop in potential here, and then you drop the rest of the way so that you can rise up again. So you rise, drop, drop, rise, drop, drop. Over here, you can rise, but because you have two different paths, when you cross either capacitor, you've got to drop all of it. So you rise V, drop all of V, rise V, drop all of V. Here you rise V, you drop part of V, and then you drop the other part of V to start over again. So V is shared in series and V is not shared in parallel. These two things right here will always lead you to algebra statements for problem solving. right? So algebra statements. Okay, so now when I want to draw an effective capacitance, what I'm trying to say is I would like to think of these two capacitors in series as actually just one capacitor that happens to have the same effective capacitance as the two capacitors in series in this case. So what this effective capacitance is going to do, though, is it's going to have a charge Q on the positive plate, which is connected to the positive terminal of the battery, and a charge negative Q on this effective capacitor. This effective capacitor is actually got a left plate and a right plate. Those charges are exactly the same charges that show up on the left plate of C1 and the right plate of C2. So in the effective capacitor, in between the two capacitor plates, is this other stuff right here, which is the right plate of C1 and the left plate of C2. But remember our Q net equals to 0 rule for individual capacitors. So here Q net is 0, right? Q and minus Q add up to 0. Over here, the only way to get the net charge rule to be 0 on individual capacitors is to make minus Q and Q. So this is the only way it's got to be. That is, in series, the charge separations are the same. This is a big deal, and I'll put it in a box. And this will give you another algebra statement. In parallel, though, it's different. So in parallel, I want to re-represent this capacitor network as a single effective capacitance. So here is that effective capacitor, and this is the battery voltage. So if the effective capacitance gets Q and minus Q, then this battery must have put a total charge of Q on the left side. So what that means is that when I separate charge Q1 on capacitor number 1 and separate the charge Q2 in general a different number on the left side capacitor plate number 2, the job of this battery was to put a certain positive charge on the left side of the effective capacitor, or it's the same charge on the left side of the parallel arrangement of capacitors. And so what this means is that the algebra statement I get here is that Q1, the charge that shows up on capacitor number 1, and Q2, the charge that shows up on capacitor 2, is the same as the charge that's separated on the effective capacitor, right? Okay, so if I take the charge separations are always the same, right? Now let me take my voltage equation here. So V, this is the battery voltage, is equal to V sub C1 plus V sub C2. So the battery's voltage is shared amongst the two capacitors. So the voltage across C1 is, remember that C is Q per V. If I solve for V in this like basic capacitor equation, I get V equals, right, Q per C, like this. So across capacitor 1, I have charge separation 1 divided by capacitance 1, right? So I just take this and I just, I'm going to talk about capacitor 1. The voltage across capacitor 1 is the charge across capacitor 1 divided by the capacitance of capacitor 1. Same thing goes for capacitor 2. But the voltage, battery voltage, is being applied over the entire effective capacitance. So this is Q over So this is the charge separated over the effective capacitance divided by the effective capacitance. In series, the charge separations are all the same. I've got Q, the same Q, the same Q, all the same. So all of these symbols actually are the same. So let me write it in terms of Q, the charge separated on the effective capacitor. So this is Q times 1 over C1 plus 1 over C2. And so you've got Q is identical on the two sides here, so 1 over C effective is 1 over C1 plus 1 over C2. So up here, the voltage is not shared in parallel. Actually, the voltages are all the same. So if I go down here and I say, since the voltages are all the same, what else can I say? Well, instead, I'm going to use this as my algebra statement, that this is a conservation of charge statement, actually. So if I look at this little like capacitor sort of relationship, another relationship is to solve for Q. So let's solve for Q. So it's just Q is C times V, right? This is true for the effective capacitor. It's true for capacitor number 1, and it's true for capacitor number 2. So if I take this charge statement here on the effective capacitance, this says that C effective, right? This is the effective capacitor here. C effective times the voltage by the battery is equal to Q1 up here. So Q1 is C1 times the voltage across C1, but the voltage across C1 is all the same. So the voltage across C1, voltage across C2, voltage across the battery, all the same value. So this is C1 voltage across the battery, or yeah, let me stop short there. Let's say it's the voltage across capacitor 1 plus C2 voltage across capacitor 2. But because the voltages are all the same, V across C1 is V, V across C2 is V. So these are also V's. So this goes C1 V, voltage across the battery, plus C2 V, voltage across the battery, C effective V. You can see that V is the common factor. So C effective equals C1 plus C2. So let's do some examples. I have two examples in mind. The first example, I'm not going to put any numbers in, but in the second example, which will be a slightly more complicated example, we'll have some numbers and have like a solid conclusion. Okay, so the first example is this. So what if I have the situation of say this. So this is kind of strange, but I've got, if you look real close, I have 3 capacitors in parallel, and I want to know if this is called, say, C1, C2, and C3, what is the effective capacitance? And I'll want to write down an expression for the effective capacitance. That is, I'm going to write down C effective equals something, right? Some function of C1, C2, and C3, right? So this is the sense in which I'll describe the effective capacitance in terms of the other quantities, the given quantities. And so it turns out that this simply, so the answer is C effective equals C1 plus C2 plus C3. It's just that the effective capacitance is just this simple summation of the 3 capacitances in a row. So the way you would solve this is you would say, If I was to hook this thing up to a battery, so let me hook it up to a battery, you would say in parallel, each of the capacitors will see the same voltage, right? Because there really is, even though there's 3 capacitors in a battery, there's really only 2 separate conductors. There is the conductor on the left, so I can draw a red line, right, all the way up through the battery, through each of the capacitors, and this whole thing on the left side is one conductor, one piece of metal that happens to have this pretty crazy shape, but it is one piece of metal. And likewise, I've got the other piece of metal. So I've only got one potential difference in this whole problem, and every separate element has the same potential difference, because potential difference, is a yeah. So, okay, so if they all see the same voltage, but they do not see the same charge separation, right? So they do not, in general, see the same charge. That's this. So I've got this essentially algebra statement that just says that, V equals VC3 equals VC2 equals VC1. That's an algebra statement. And another algebra statement is they don't see the same charge, but there is an overall charge conservation. That is, the charge Q that separates over the effective capacitor is equal to the charge that separates over capacitor 1 plus the charge that separates over capacitor 2 plus the charge that separates over capacitor 3. And if you couple this with C equals Q over V, which means, right, this is the definition of any of the capacitances. This is the charge separated over that capacitor if that's the potential difference. So that means that over any separate capacitor, including the effective capacitor, Q is CV, so this is CV, but it's for the effective capacitor. This is C1V, this is C2V plus C3V, and I have put in the fact that they all see the same voltage. So capacitor 1 sees voltage V, capacitor 2 sees the same voltage V, capacitor 3 sees the same voltage V. So V is common, it's a common factor in all of the terms, and so you get C effective equals just C1 plus C2 plus C3. And if I went up and added a C4, you would just end up with a C4, right? So, and you notice it doesn't matter which order the capacitors are in. I put C4 up above C1, so it kind of looks like I'd have to add it in front if I follow a pattern. But you know that the summation, right? Addition is commutative, so I don't have a particular order for these. Okay, so that's an example. Here's another example. I described having an example that has... So the second example is, I'm calling it a mixed example. I've got this capacitor network of 3 capacitors called C1, C2, C3, connected in this way. This is its topology. And they're connected up to a battery that provides voltage V. C1 is a 1 microfarad capacitance. C2 is 2 microfarads, twice as capacitive. And C3 is the most capacitive. It has the most capacity to store charge for a given voltage. And these are the values. So 1 microfarad, 2 microfarads, 3 microfarads. And the potential difference provided by the battery is 3 volts. And the question is what is the charge that's separated on capacitor number 2? Right? What is the charge on capacitor number 2? So let's let's think directly about the charge on capacitor number 2. So off to the side, we have the definition of capacitance, which means applied to capacitor number 2, this is the capacitance of number 2, must be the charge separated over number 2, divided by the voltage across capacitor number 2, right? So if I can, so I already know, right, Q2 is what I want to know. So that means that Q2 is equal to C2 times V2, right? C2, I've got a number for it, but V2, I do not have a number for it. I don't know what the voltage is across the capacitor number 2. I've got a voltage, 3 volts, but this 3 volts is not across C2 by itself. This voltage is actually across some effective capacitance, right? From the sort of bottoms of both of C2 and C3 and the top of C1. So there's some other stuff going on. It's like, you know, it's a mixed example. It's got lots of capacitance in it. But anyhow, so I don't know. So I want this. I know the capacitance of number 2 it's given, but I still don't know the voltage, right? So if I could figure out the voltage across number 2, then I know how to solve our problem. Okay, so I'm kind of at a dead end a little bit, right? Is there a way to get this voltage across number 2? So let's think in terms of voltages. So the voltage, 3 volts, right? This capital V, which is 3 volts, it's equal to, it turns out, it's the voltage across capacitor 1 plus the voltage across either capacitor 2 or capacitor 3, because they're in parallel, they have the same voltages. In particular, I really want to know what V2 is, so I'm not going to introduce V3, I'm going to introduce V2. So let me just put V2. So, right, so I am finished. It is a mistake for you to also include V3. That's not correct. It's either V2 or V3. Yeah, so, and I apologize. I shouldn't have wrote V sub C1. I should just write V1. So let me, yeah, I'll fix it in the next line. So, can I fix it in the next line? Sure. So this is, I'll just rewrite it. V1 plus V2, but not V3. So I don't know V1, I wish I knew V2, and I know that capital V is 3 volts. So I still have 2 unknowns. I have too many unknowns, which is what happened over here. I have 2 unknowns, 1 equation kind of stuff. I just don't have enough equations yet in my unknowns. But anyhow, I really want to know that. I still don't know this, but I do know what they add up to. It's that. Okay, so I have this equation. So let me mess around. So this voltage is across the effective capacitance. Is that going to help me? Let's see. So remembering my C equals Q per V thing. So let me rewrite everything. So V1, for example, so solving for V, you know, it'll be Q per C. It'll be the charge separated over number 1 divided by capacitance of number 1, so C1. So that's that could fit here. And likewise, there's a really similar thing. You would just write Q2 over C2, right? Oh, I actually already kind of had that over here. But anyway, so let me put these here and let's see where I can get. So V1 is Q1 over C1, and V2 is Q2 over C2, and that is equal to 3 volts, like this. Okay, so I still don't have enough information because I don't actually know what the charge separated over capacitor number 1 is. Right? I know what C1 is, I know what C2 is, I want to know what Q2 is, but I don't know what Q1 is. So I still don't have enough information. Right? It's like I have an equation, but with too many unknowns every time. Okay, so let's go on a little bit. So we just went through all this stuff in the previous video and videos, and the in this video I showed you how to calculate what's called an effective capacitance. So let's go that route. This 3 volts is over the capacitor network that has some big effective capacitance. So I'm imagining replacing from here to here with this effective capacitance. So let me see what that gets me. That 3 volts is actually being applied over the entire effective capacitor. So let me do it that way. So there is a charge separated over the effective capacitance divided by the effective capacitance, and that's going to be what the 3 volts is. So I can now update my relationships amongst interesting quantities. So what's Q effective? I don't know. I do know that this is all 3 volts. I don't know Q1, I don't know Q2, I don't know Q effective, and I don't know C effective. But I can figure out C effective. So here's a reason that I need to start thinking in terms of the network. I can't think in terms of individual capacitances and get far enough. So let's get C effective. So C effective is, I'm going to get it by realizing that C1 is in series with the parallel combo of C2 and C3. That is, C1 is in series with the parallel combination of C2 and C3. Right, C1 is in series with the parallel combination of C2 and C3. So the parallel combination is really easy. So C1 is in series with a capacitance, the parallel capacitance of C2 and C3, so it'll be C2 plus C3. C1 is in series with a capacitor, like a sub-effective C2 plus C3. So C effective, I'm going to write down what it's got to be. It's got to be the series combo, looks like 1 over C1, plus 1 over the parallel combo, C2 plus C3, like this. That's a 2. Don't forget raised to the minus 1, or else your dimensions are all messed up and you will not get the right answer, no matter, yeah, so it's got to have that minus 1. So this is something I know all the values to get if I want. So I could put in there. And what this will give me actually is if I just use this part, I get Q effective equals 3 volts times C effective, which I can get a number for. So that's somewhere I can take a step. Okay. So when I take this step, cool. So yeah, so I know Q effective. So let's go ahead and get C effective. So C effective is, so C1 is 1 microfarad. So this is 1 over 1 microfarad plus 1 over 5 microfarads, right? 2 microfarads plus 3 microfarads. And I'll raise to the minus 1 power. And if I multiply 5 over 5, here I can have common denominators, so I can add the 2 fractions. So 5 over 5 plus 1 over 5 is 6 over 5. Right? And flipping over this ratio is really simple, so it's 5 over 6 microfarads. That's the effective capacitance. So if the charge separated over the effective capacitance here, you might say that that's Q effective on top and negative Q effective on the bottom. That's the charge separation, is 3 volts times this business here, so 3 volts times 5 over 6 microfarads. And a volt times a farad is a coulomb, so this is microcoulombs. So 3 over 6 is a half. Half of 5 is half of 5. So we'll go 5 over 2 microcoulombs. So that 5 over 2 microcoulombs is sitting on the upper plate of the effective capacitance, which means that it's also sitting here. They are going to be the same. And actually, here, the negative Q effective is split between C2 and C3. I'm not sure how they're split. It's not half and half. It could be 2/3 and 1/3 or something like that. But I'm not sure how it is. I just know that it is split that way. That's how effective capacitances work. This is charge conservation. Okay, so I've got so what I just showed you is actually this is also, right, thinking about charge, this is also the charge separated over capacitor number 1. And this actually is the crux. This is the crux decision to make, because once I say that I know Q1, now if I look at this expression, I know everything except for Q2. So that's what I'm going to do is when I make this decision right here, this is the big crux, is that the effective charge on this capacitor network is actually the same as the charge separated on capacitor number 1, which is a charge conservation decision. Then I've got the charge. So now I'll go back here, right? And it doesn't really matter. I'm going to use 3 volts equals this plus this, where I know one of the Q's, and I'm going to solve for Q2. So if I take this line down, I hope you can see that 3 volts minus Q1 over C1 multiplied by C2 is equal to Q2. All I did was I took this, which is equal to, skip this thing, equal to 3 volts, and I subtracted Q1 over C1 to sit next to 3 volts, and I had Q2 over C2 left over. I multiply the C2 up, and I left over with Q2. So this is my sort of multi-algebra steps in a row. But the thing is I know every value here, and this is originally what I wanted. So let's fill it in. So C2 is 2 microfarads. I've got 3 volts minus, this is the potential difference across C1 actually. So the potential difference across capacitor number 1 is 5/2 microcoulombs divided by C1 is 1 microfarad, right? That's the difference there. And then so that's what Q2 is, and I'll just keep going. So 5/2 over 1 is 5/2. The micros cancel. A coulomb per farad is actually a volt. That's the SI unit magic. And I get 2 microfarads times 3 volts minus 5/2 volts. So what this means, right, 5/2 is 2.5, so half a volt is left over, and half a volt times 2 microfarads is 1 microcoulomb. I think that's the right answer. Yeah, so Q2 is 1 microcoulomb. I had to make a judgment call, though, that was crux. I wandered around for a little while. I was meeting dead ends. I was trying not to think of the capacitor network in this effective way. I was trying to think of individual capacitances, but I wasn't making any traction. So I'm like, what the hell? Let me bring up the effective capacitance. And then I think in terms of this sort of overall capacitance, where the overall capacitance plate is just identical to the upper plate. The lower plate is actually the combination of the two lower plates down here. Yeah. Okay, and yeah, so that was the crux kind of decision-making point, and then I actually ended up being able to continue. There's many ways to wander around in here. This is one of those examples of just knowing the solution, watching it happen in a solutions manual, like, oh, okay, I believe that, oh, okay, I believe that. But the problem is you didn't make any of the decisions on your own. You didn't ever experience ultimately finding dead ends and deciding, actually, I'm not sure that I can continue in any way. You didn't have any experience being creative, trying to be like, okay, well, I got to think a little bit up outside of the individual capacitors and start thinking about combinations of capacitances. So you've got to have these experiences, and you have to ultimately, like, this is not the only way to pass through to get to Q2 from the starting point. Just like there are many, many ways to get between two places in a city, you know? And the Google Maps version, which is the solutions guide version, even though it might be the most succinct and efficient, it's not the only one. And you're not always going to come up with the most efficient solution to problems. So the way that you become good at finding solutions to problems, efficient or not, is by messing around on your own, lost, but having the tenacity to find yourself constantly and to sort of learn things over and over again, discover new meanings in things that you thought you had down really well. Yeah, so this stuff's really hard. And this is only one example of a capacitor network with 3. Like, what if the problem was like this instead? They're really different, but they have 3 capacitors. Solving this is going to seem really similar to solving this. You won't have the same crux move, though. There's some similarities, but they're still different. Here, actually, this is the top plate of this effective capacitance. This is the bottom plate of the effective capacitance. And this is some internal thing that's interesting in and of itself. But so when you think of effective capacitance, right, if this is the effective capacitor, the upper plate is this one and this one. The lower plate is this one and this one. Yeah, you'll have to, yeah, okay.